Current loop technology has been used for analog sensors for the past 4 decades to transmit important process data to the control system, whether that system is a DCS, or distributed control system, a PLC, or programmable logic controller, or a single-loop controller. Current loop data transmission is simple and cost-effective. Only a small amount of current, 4 to 20 milliamps to be exact, is required over a single pair of wires for each current loop sensor. One 2-amp, 24-volt DC power supply can drive dozens of sensors. For current loop analog sensors, the lowest measurable process value is called the lower range limit, or LRL. The analog sensor will output 4 milliamps at this 0% reading. The highest measurable process value is called the upper range limit, or URL. The analog sensor will output 20 milliamps at this 100% reading. Many analog sensors, such as pressure and temperature sensors, are inexpensive, and good quality sensors can be purchased for $100 to $500 US. More complex flow, level, and analytical sensors do cost more, but these still only require a single pair of wires to allow the process variable, or measured variable, to be transmitted to the control system. Another positive feature of analog sensors and transmitters is that the signal can be carried a great distance along a single pair of wires with little or no signal loss. A current signal can be transmitted up to 1,000 meters through 18-gauge wires with no appreciable signal loss. Lastly, 4 to 20 milliamp current loop signals provide a basic level of diagnostics. Since 0% equals a 4 milliamp signal, a broken wire would break the circuit, and 0 milliamps would be sensed. This live zero feature, where 0% is equal to a value of greater than 0 milliamps, allows the control system to detect a broken wire at 0 milliamps. But analog sensors can only send one value over a single pair of wires to the control system, and the granularity or precision of the data is limited by the type of analog to digital converter, or A to D converter, used by the control system electronics. However, with modern electronics, this is not as much of an issue. An A and D converter with 16-bit precision can report the range of values for an analog sensor in 65,535 increments. This means that for a 0 to 1,000 psi pressure sensor, the granularity of the signal value is 1,000 divided by 65,535, or 0.015 psi. This level of precision would be sufficient for most applications. Before we answer the question of what Hart is, let's look quickly at another analog device, the analog telephone. Analog telephone communication is similar to analog sensor signals used in industrial plants. Analog telephone lines transmit voice as 48-volt DC electrical signals. When you speak into the handset of your phone, the microphone converts the sound waves into analog electrical waves. These waves propagate over the telephone line to their destination. The receiving phone then converts the electrical signals back into sound waves through the speaker of the handset. One pair of copper wires for voice transmission and one conversation, or transmitted value, at a time, just like an industrial analog sensor. In the late 1970s, Bell Labs invented the Bell 202 modem standard. In 1980, the Bell 202 standard was adopted as the communication standard for subsea oil and gas production control systems. Bell 202 specifies a modulation method known as audio frequency shift keying, or AFSK, to encode and transfer digital data at a rate of 12,000 bits per second, half duplex, meaning transmission only in one direction at a time. Basically, it provides a continuous signal as an AC sine wave that shifts its frequency from 12,000 Hz, indicating a binary value of 1, to 2200 Hz to indicate a binary value of 0. Here's the kicker. If we superimpose a Bell 202 signal on top of a standard analog telephone line signal, we gain the ability to send digital data and analog data at the same time on the same pair of wires. This was used to transmit the caller's telephone number along with the voice call. This feature is well known as caller ID. So, what if we superimposed a Bell 202 signal on top of a standard analog sensor line signal? We gain the ability to send digital data and analog data at the same time on the same pair of wires. This is Hart communication. With Hart, we can send analog data, the measured value of the process variable, along with digitally transmitted data, such as a tag name, or calibration settings, or sensor diagnostics. This would be a real productivity enhancement for the process plant. And because Hart-enabled sensors require only a single pair of wires for communication, to upgrade an existing non-Hart sensor loop to a Hart-enabled loop, no wiring changes are required. Of course, both the sensor and the analog input card at the controller would need to support Hart. The good news is that Hart is built into most commercially available analog sensors, and Hart-enabled analog input cards are available from nearly all DCS and PLC manufacturers. There are even add-on hardware devices to convert your Hart sensors into wireless transmitters. Now that we know what Hart is, let's finish the discussion of how Hart works. First, Hart is an acronym for Highway Addressable Remote Transducer. This simply means that a small network can be formed with up to 63 Hart devices, each having its own address, or node number. Because a sensor can be remotely accessed using Hart, the name really does say it all. Highway, or network, sensor, also called a transducer, that has an address so that it can be accessed remotely and directly. The remote capability of Hart sensors is very useful and powerful. In this diagram, we see a Hart sensor connected to a PLC analog input card. We can access data in the sensor remotely using the Hart Communication Protocol from the PLC programming software. That means we do not have to be at the location of the sensor to access its data. We can configure, calibrate, and retrieve diagnostic data from a control room or other location where the Hart data is accessible. Data from a Hart sensor must be requested by the master node, which controls all conversations on the loop. The master node is typically the DCS or PLC analog input card that the sensor is wired to. Each message from the master includes the request type, such as send measurement value, the node number of the sensor the message is intended for, and any data that needs to be transmitted to the sensor, like a new value for the upper range limit. By using a handheld programming and configuration device, often called a Hart communicator, the sensor data can be accessed wherever the opportunity exists to connect the handheld device in parallel to the loop wires. This can be in a junction box, marshalling panel, or at the sensor itself. So if a sensor is in an inaccessible or hazardous area, configuration or maintenance of the sensor can be done from a safe, remote location. Networking Hart devices in most control systems applications is not practiced, because of its limited speed and its cumbersome multi-drop network topology, we generally assign only one node or sensor to each Hart signal loop. Fortunately, Hart allows for multiple master nodes, so that the control system and a handheld communicator can both be connected to the loop and can communicate with the device at the same time. With Hart, the analog 4 to 20 milliamp signal and the digital Hart protocol are both available to the control system and instrument technician. If a sensor loop is upgraded from analog only to analog plus Hart, the control system programming and configuration for the measurement value can stay the same. You can imagine that superimposing an AC signal on top of a DC signal might interfere with the 4 to 20 milliamp signal, but this is not the case. The AC Hart sine wave oscillates at either 1200 Hz for a 1 value or at 2200 Hz for a 0 value. The amplitude of the AC sine wave remains the same, and for every oscillation, the amplitude of the first half of each sine wave above the DC current curve exactly equals the amplitude of the second half of each sine wave below the DC current. The net effect of the sine wave is then 0. So, the analog value of the sensor measurement data is not affected by the Hart signal, just as a telephone voice conversation is not affected by the caller ID signal using the same Bell 202 protocol. Each Hart device is capable of sending and receiving 35 to 50 different information items, including the process variable, that is the same measurement value as provided by the 4 to 20 milliamp analog signal, device status, diagnostic alerts like sensor value under range, basic configuration parameters like upper and lower range limits, and the tag name of the device. Hart is a perfect choice for multivariable instruments like mass flow meters, where mass flow, volumetric flow, temperature, and density can all be communicated to the control system over a single cable. The Hart protocol is governed by a vendor-independent association, the Hart Communication Foundation, so Hart sensors from any manufacturer can be interchanged with those of other manufacturers. This makes implementation, maintenance, and troubleshooting very easy. Also, Hart is used extensively for final control devices, such as control valve positioners, with the same benefits and diagnostic capabilities. Even though the Hart standard requires manufacturers to provide a minimum number of specific data items with every Hart sensor, vendors can also extend the data set to include vendor-specific items, like sensor model numbers, or firmware versions or advanced diagnostic counters. In order for the control system to recognize the type and values for these custom data, a special description file called a data description or DD file is required. This file is loaded on the DCS or PLC configuration station or downloaded to the handheld communicator and becomes directly associated to the sensor. This file simply allows the data stream from the sensor to be correctly parsed or interpreted and allow the technician or engineer to make the correct requests for sensor data. To review, Hart is a digital data communication protocol that is layered on top of a traditional analog 4 to 20 milliamp signal, which provides advanced data retrieval and configuration options to be executed remotely from a DCS or PLC system, or from a handheld communicator. Hart communicates over a single pair of wires, so adding Hart to an existing 4 to 20 milliamp sensor loop requires no wiring modification. Only the hardware at the analog input card and the sensor electronics may need to be upgraded so that the Hart functionality is provided. a high percentage of sensors already installed in 4 to 20 milliamp loops are already Hart-enabled. Hart may be the field bus you already have in your plant. Through simple configuration, a wealth of new process data and diagnostic capability can be obtained with a minimum of effort and expense.